Swayam Prabha. Digital India. Educated India.
Hello students, welcome to this lecture. In today's lecture, we will continue our discussion on molecular spectroscopy. So far we have discussed about rotational spectroscopy and vibrational spectroscopy. Now in today's lecture, we will start our discussion on electronic spectroscopy. We saw in the case of rotational spectroscopy, we used microwave radiation because that radiation had just about enough energy to induce a rotational change in the rotational energy levels of molecule. For vibrational energy levels, to show vibrational excitations, we needed more energy. So, therefore, we used infrared radiation. Now, we have to find out that part of electromagnetic radiation which has enough energy to induce an electronic change in the molecule. Only when there is an electronic change in the molecule and associated change in the electric dipole moment in the molecule would start interacting with the electromagnetic radiation, and then we get the transition and the spectroscopy is successful. So, in today's discussion, we will first talk about a few simple systems. In particular, first we will discuss about the electronic spectroscopy of atoms. Before we go for many electronic atoms, we would first refresh our memory on hydrogen atom, because this problem is what we have already solved exactly, and we will just look at this the results of hydrogen atoms eigenfunctions and eigenvalues, and see how we can explain the hydrogen atoms emission spectrum. So, if you remember, we have after solving the Schrodinger equation of hydrogen atom, which is a one electron problem, we saw that the energy levels are quantized. The ground energy level, they are all quantized with quantum number n. So, the lowest value of n is 1, and corresponding to the quantum number n, which we call principal quantum number, we also have azimuthal quantum numbers L going from 0 to n minus 1. So, therefore, in this case, when n is 1, we have L value is 0. So, therefore, this is your 1s orbital, and for when n equals 2, we can have 2s or 2p, that means L is 0 or L is 1. When n is 3, we have 3s, 3p and 3d, and so on and so forth. One important feature is that only for hydrogen atom, because there is only one electron, we have the energy levels which depend only on the principal quantum number and not on the orbital quantum number L. For all other atoms, that means all multi-electronic atoms, the energy levels depend both on n, the principal quantum number, and the azimuthal quantum number L. Only for hydrogen atom, it has only n dependence. So, therefore, the 2s and 2p levels are degenerate. As we go higher and higher n levels, the relative energy spacing increases, and when we go for n equals very large or n equals infinite, we approach 0 energy. All the discrete states that you see here in this picture, they have negative energy, suggesting they are bound state, or they have stability, because in this case electron is bound to the nucleus. But when energy is 0 or energy is positive, this is the situation where the electron has completely left the field of the nucleus, and it is a free nucleus. So, there is no interaction between the electron and the nucleus. So, therefore, the energy is either 0 or positive or some continuous value. We do not have quantized energy levels in those cases. Looking at these energy levels, we could explain the emission spectrum of hydrogen atom, which was a major problem that gave rise to the birth of quantum mechanics. The general expression of this emission line is given by this Rydberg's formula, where you have RH as the Rydberg's constant and N1 and N2 are the two energy quantum numbers from where the emission is starting and to where the emission is going. So, when N1 is 1 and N2 equals 2 or 3 or higher values, we call these lines as Lyman series. and this Lyman transition happens. So, that means if you consider an emission spectrum, so you go from 2 to 1 or 3 to 1, 4 to 1. So, in this case all these transitions occur at ultraviolet radiation. So, as you can see, there is a huge gap between the energy levels of n equals 1 and the rest of the energy level. So, it requires more energy. So, therefore, it happens at ultraviolet. So, when we do see emission, the ultraviolet radiation gets emitted. If we consider absorption, we must provide ultraviolet radiation to undergo this transition from n equals 1 to higher values of n. Coming to n equals 2, so n1 equals 2. So, from the second level we can go to 3, 4 and so on. So, for the absorption, and for emission we from n3 or 4 or 5 we come back to a 2 level. So, suppose if I draw some lines. So, these are Balmer series lines. You can see compared to the Lyman series lines, Balmer series has much lower energy, and this transition occurs at visible range, which has lower energy. Now, going to the next levels, you see n1, 3, 4 and 5, they are all very closely spaced. So, you can see this is these are the emissions that you see from higher level to n equals 3, and these energies you can see they are much smaller compared to the energies of the Balmer series or energy of the Lyman series, and they are called Paschen series, and they occur at infrared radiation. Infrared radiation is the radiation that we are using for vibrating the molecule. So, therefore, when we go to excited electronic energy levels, the energy levels become much smaller the difference in the energy levels get much smaller, and then that transition occurs at infrared region. So, of course, when you go for higher series bracket of P-fund, and then you see emission at even lower energy, and they occur at far infrared. So, this was about the electronic spectroscopy of hydrogen atom. One thing that was very simple in case of hydrogen atom is that the energy level depended only on the n, the principal quantum number, whereas it had no dependence on the orbital angular momentum of the orbital that we are talking about. So, therefore, the selection rules became trivial for that. But when we go beyond hydrogen atom or for multi-electronic atom, the selection rule becomes very important, because now the energy levels are different for different orbitals. So, therefore, we need to know which transitions are allowed and which transitions are not allowed. To do that discussion, we will now look at electronic spectroscopy selection rule. Like the discussion that we had for rotational or vibrational spectroscopy, we start from the transition dipole moment, which says that I have the initial state psi initial and the system goes to the psi final, and it is the electric dipole moment of the molecule that undergoes a change during this transition, and therefore, it interacts with the electromagnetic radiation and the transition occurs. So, mu is my electric dipole moment, which in this case is given by as minus E, which is the charge of the electron, r is the distance of the electron from the nucleus. Now, we have already discussed in case of vibrational spectroscopy, the selection rules are obtained from symmetry argument, which say that only when those kind of transitions are allowed when the transition dipole moment or the direct product of these components in the transition dipole moment, the direct product of this should be totally symmetric with respect to all symmetry operations of that group. Now, if you remember, in case of water, when we are discussing vibrational spectroscopy, the molecule belonged to C2V point group, and we discussed that the totally symmetric representation in that point group was A1 symmetry, because no matter which symmetry operation you do under A1 irreducible representation, the system is symmetric to all the symmetry operations. So, therefore, that was total symmetric representation. What about atoms? Atoms belong to the so called full rotation group, R3. We will discuss what they are, or what are the elements that we require from this R3 group to carry out our discussion. So, first of all, atom belongs to this full rotation group R3, and whose basis of this group are simple the orbital angular momentum of the atom. So, that means the spherical harmonics, which were the eigenfunction of the angular momentum operators, they can be used as the basis for the full rotation group R3. Now, we would consider some symmetry operation under R3, because mind you the selection rule tells that transition is symmetric, that transition is allowed only when the transition dipole moment becomes totally symmetric with respect to all symmetry operation of that group. So, we will consider a few symmetry operations and see what are the necessary conditions for a transition to occur. The first symmetry check that we will carry out is the inversion symmetry, or we also would use the parity. What do I mean by inversion? Inversion simply suggests that if I take x and carry out its do an inversion operation, x goes to minus x, or y goes to minus y, z goes to minus z, and if I have a function which has x, y, z altogether, then the all three functions go to their negative values. Now, we know that some functions, when I change from x to minus x, the function does not change. So, if f of x is equal to f of minus x, then we call that function an even function, and if f of x becomes minus of f of minus x, then we call that function odd function, and if none of this is true, then that function does not have a definite parity. So, an even function has is symmetric with respect to parity, and odd function is antisymmetric with respect to parity. Now, let us look at the three components in this transition dipole moment expression. First, we will consider the dipole moment operator mu. As we see that electric dipole moment operator mu is given by minus ER. Now, R is the vector that connects the nucleus to the electron. So, if I carry out, since it is in the form of r to the power 1, so therefore, you know that this has parity of minus 1. So, that means this is an odd function. Mu is an odd function. What about psi initial or psi final? So, we are talking about what is our psi initial? This is one of the orbitals. Suppose we are considering we will make a transition from 1s orbital to 2s orbital, or 1s orbital to 3s, or 1s to 3p, and so on so forth. So, therefore, the initial and the final states are some orbitals, atomic orbitals. So, the parity of these orbitals is given us. So, an orbital with orbital angular momentum L has a parity of minus 1 to the power L. So, that means when L is 0, this is an even function. When L is 1, this is an odd function. So, when L is 0, this is an s orbital. When L is 1, this is a p orbital, this is odd, and so on and so forth. So, d orbital is an even function, f orbital is an odd function, and so on and so forth. So, the orbital's parity goes as minus 1 to the power L. Now, let us see, suppose it goes from initial state of Li to final state of Lf. So, what will be the parity of the transition dipole moment? The parity would be given as minus 1 to the power Lf, that is the parity of the final state, multiplied by minus 1, which is the parity of the operator mu, minus 1 to the power Li, which is the parity of the initial state. So, when I look at this, because I have this minus 1, so therefore, to make and I am supposed to get plus 1, because it has to be totally symmetric, the total electric dipole transition dipole moment must be totally symmetric. So, therefore, I should get plus 1, and this is possible only when Li and Lf have are of opposite parity. That means, if Li is an even function, Lf must be odd and vice versa. So, this is this famous Laporte selection rule, which says that the only allowed electric dipole transitions are those which involve a change in parity. So, that means I can go from S to P, but I cannot go from S to D according to this parity selection rule. Now, we obtained one condition. Now, let us look at other symmetry operations. The next symmetry operation that we are going to do is that the orbital symmetry, or we call it the rotational symmetry. So, now an orbital with orbital angular momentum L spans the irreducible representation corresponding to gamma to the power L. So, this is the irreducible representation under R3 point group. So, if this gamma L is the irreducible representation for the orbital with orbital angular momentum L. Under that, the electric dipole moment mu, which is minus e into r, which the function is actually a translational, this is simply Cartesian a position function raised to the power 1, which is similar to the symmetry of a translational motion. So, therefore, its symmetry is gamma to the power 1. Under this condition, gamma to the power what will be the totally symmetric representation? That would be gamma to the gamma 0. Gamma 0 is the totally symmetric representation. Now, looking at we will consider this expression here and find out what is the symmetry of the transition dipole moment under this. So, again we are going from Li to Lf. So, therefore, the symmetry of the transition dipole moment will be gamma L to the power gamma Lf, direct product of gamma 1, because that is the symmetry of the operator, and this is gamma Li. Now, I have these two direct products to consider. Here I would use one important relation, that is, if I have gamma L1 and gamma L2, the direct product of them is given by the following relation: gamma L1 plus L2 plus gamma L1 minus L2, absolute value of L1 minus L2, and this series goes as L1 plus L2, L1 plus L2 minus 1, L1 plus L2 minus 2, and so on, so forth. To give one example, if I consider gamma 1 into gamma 2, this would be L1 plus L2 is 3. So, therefore, this is gamma 3 plus gamma and what will be the last value? The last value will be L1 minus L2. So, therefore, 2 minus 1, that will be gamma 1. So, in the step of 1, so I have only gamma 2. So, gamma 3, gamma 2, gamma 1. So, in under this symmetry, so since I am telling that gamma an orbital with orbital angular momentum L belongs to gamma L symmetry. So, therefore, you can see this is a p orbital, this is a d orbital, this is an f orbital. All right. So, now since we just take one more example, gamma 2, that means a p orbital, sorry, a d orbital and a d orbital. So, in this case L1 plus L2 is 4, L1 minus L2 is 0, and in between we have gamma 3, gamma 2 plus gamma 1. So, this is how this it works. So, therefore, let us consider our this is the direct product that we have to evaluate. When we do this, so before we go to gamma Lf, let us first consider this gamma Li into gamma 1. You see this would give me gamma Li plus 1, gamma Li minus 1 plus gamma Li, to make it in the usual order. Li plus 1, Li minus 1. Now, these three representations will be multiplied with gamma Lf. So, I would have to see gamma Li plus 1 when I multiply it with make a direct product with gamma Lf, this must contain gamma 0, then only this will be totally symmetric. But we would see that it will contain gamma 0 only when Li plus 1 is Lf. If the two terms are of same symmetry, then only that direct product will have gamma 0, as you can see here in this example. Gamma 2 product had gamma 0, whereas gamma 1 and gamma 2 did not have gamma 0. So, therefore, this condition is necessary, and similarly I can say Li minus 1, this will contain gamma 0 only when Li minus 1 is Lf, and the third gamma Li into gamma Lf, this will contain gamma 0 when Li equals Lf. So, the condition that I am getting is that this will have this transition dipole moment will be totally symmetric only when delta L equals plus minus 1 or delta L equals 0. But there is a problem. The problem is when delta L equals 0, this violates Laporte selection rule, which requires a change in the parity. So, therefore, delta L equals 0 transition is gone. So, I am left with delta L equals plus transition. So, we add to our selection rule box as delta L equals plus or minus 1 as the next necessary condition for the transition to be seen. Now, we will look at the next symmetry. So, we talked about L, but we know when you have an electron, it not only has the azimuthal quantum number or the orbital angular momentum, it also has the magnetic quantum number ml, which depends on L. So, now we will consider the selection rule. We will consider the selection rule corresponding to ml. If you remember, the solution of hydrogen atoms atom problem, you would see that we had the radial solution and the angular solution. The angular solution had the L part, which depended on theta and phi, and we had on the m part, which depended only on the phi coordinate of the spherical polar system. Now, for ml magnetic quantum number, the corresponding wave function is e to the power I ml phi. Of course, now we are considering does not matter which value of L our electron is, as long as it has a given ml value, we know that the corresponding function will be e to the power I ml phi. So, suppose we have we are starting from mli quantum number to mlf quantum number in this transition. So, in this so therefore, we have to find out what will be the transition dipole moments value. So, if I want to get this transition dipole moment value, and just before that I must know what is mu. Mu, you know that it is minus E r, and suppose I am for the time being, let us consider that I am using z polarized light. So, therefore, I am considering mu z as E minus E z, which is E r cosine theta. Theta and phi are the usual definition that we introduced in the spherical coordinate system. Now, for the time being, we are considering only mu z, and then we will write down this integral psi final, which is e to the power minus I ml f phi, the mu which is minus E r cosine theta, and psi initial, which is e to the power minus I m l I phi, and then I am integrating this. Of course, I am ignoring what happens to the theta and r term, because I am only considering this d phi, whose limit which phi goes from 0 to 2 pi. Since this operator part contains r and cosine theta, so I am taking them out of this integration, and I am telling that this is proportional to now if you look at this integrand here, you would see that the result of this integration will be 0 unless MLI is equal to MLF, because for MLI and MLF both can have either integer values or half integer values. So therefore the difference is always going to be an integer, and when I integrate this e to the power I and phi, I would always get 0 unless this is equal. So therefore this will survive only when delta m equals 0. This is one condition, but mind you, we just took mu z. We have not considered mu x and mu y. So if we consider that, the operator will become er sin theta sin phi minus er sin theta cos phi, and when I use these expressions in this integral, I would see delta m equals plus or minus 1 would come out as the selection rule. So now we have got the selection rule with respect to the magnetic quantum number, and we can add that to our selection rule box, where delta ml equals 0 or plus minus 1 at the allowed transition. Now we have finally one more selection rule to worry about, and that concerns that not the electron that we have not only has a principal quantum number, an orbital quantum number and a magnetic quantum number, but it also has a spin quantum number. The spin of the system is spin of the system, since we are talking about an electron, is by nature it is s equals half. So therefore it has got 2 spin state, and the formulation, the solution and the formulation that we have had here does not consider the relativistic effects, for example, the spin orbit coupling into account. Under that approximation, when there is no spin orbit coupling, or when the spin orbit coupling can be negligible or we can ignore, in that case and there exists another selection rule that the transition will not involve a change in the spin multiplicity. That means, if we are in a singlet state, we would always go to another singlet state, or if we are in triplet state, we will always go to another triplet state. The spin multiplicity should remain conserved during the transition. So that will be our next selection rule in the selection rule box. So these are the overall selection rules that we have for electronic spectroscopy of an atom. Of course, all these selections rule, for example, delta S equals 0 selection rule breaks down when we have heavy strong spin orbit coupling, and other selection rules also have their limitations when additional couplings are considered into the picture. Now, one important information. So far, when we consider the transition, we always considered electric dipole moment as the operator which takes us from initial state to the final state. But we also should clarify that we can also use magnetic dipole moment to represent the same transition. So we have, of course, the electric dipole moment. We can also use, as I said, magnetic dipole moment. Or in some cases, we also can use electric quadrupole moment. These are different momenta that can that can allow the transition to occur. The reason why we consider electric dipole moment is that its interaction with the electromagnetic field is the strongest. When you consider magnetic dipole moment, the coupling between the magnetic dipole moment of the molecule and the electromagnetic magnetic dipole moment of the electromagnetic radiation is about 10 to the power 5 times weaker compared to the electric dipole moment, and electric quadrupole moment is about 10 to the power 8 times weaker compared to the electric dipole moment. So therefore, even if we can see transition because of these properties of the molecule, but still they are so weak that the electric dipole moment transitions dominate the picture. But they become very important when electric, for some reason the symmetry does not allow for an electric dipole transition. In that case, in those cases electric quadrupole moment or magnetic dipole moment can come into picture, because these two they follow different selection rule compared to the selection rules that we discussed for electric dipole moment. So, when for some reason if electric dipole moment does not allow this transition to occur, if the selection rule allows, we can use magnetic dipole moment or electric quadrupole moment to see those transitions, but those transitions are normally rather weak. So, in today's lecture we discussed about the selection rules and in electronic spectroscopy, and we will carry out our discussion in the next class on the electronic spectroscopy of many electronic atoms. Thank you for your attention.